Today we're going to talk about finding the rational zeros and the rational root theorem. Sometimes we will not be told what to divide our polynomials by in order to find the roots. For a situation where we need to find all the roots, we can use what's called the rational root theorem. So the rational root theorem, if f of x, and this is polynomial form right here, has integer coefficients, then every rational zero of f of x has the following form. So p over q, which stands for factors of the constant term over factors of the leading coefficient. So this will help us get our possible rational zeros of our polynomial equation. So unlike the other day, we were given a zero or given a factor and then we had to find the other factors. Now we're not going to be given those zeros and we want to find all the solutions. So this first one, we're just going to practice listing the possible rational zeros. And remember, a rational number is a number that can be written as a fraction or has a terminating or repeating decimal. So for this, here's our polynomial equation, and for our polynomial equation, we want to list the possible rational zeros. So the first thing we need to do is figure out what is our constant and the leading coefficient. So the constant, remember, is the one without the variable, so 10, and the leading coefficient is what's in front of the lead term, which in this case is 1. So we want the factors of 10 over the factors of 1. So factors of 10, of course, are plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 10. And then factors of 1 are plus or minus just 1. Remember, if you don't remember your factors, you can always go to your calculator and use your calculator to help you by plugging into your y equals 10 divided by x, and then you could go to the table to look at the factors. So again, you can see those starting with a 1. All right, so back here. So then we want our possible rational roots, which is the same thing as the zeros or solutions or x-intercepts. So the possible rational roots, which I always label just as P, R, R, is plus or minus factors of the constant term 1, plus or minus 2, plus or minus 5, plus or minus 10, all divided by factors of the leading coefficient, so plus or minus 1. So when you write this out, that means you're dividing each of these terms by 1 in this case, so I'm just going to write the plus or minus in front and use parentheses, so plus or minus 1, 2, 5, and 10. These are the possible rational roots. Doesn't mean they're the actual rational roots, which we'll talk about in just a minute. So go ahead and pause the video, do number 2 on your own when you're done on pause, and we'll take a look. So looking at question number 2, our constant is, in this case, 6. So we're going to have to find factors of 6. And the leading coefficient is 9. So factors of 6 are plus or minus 1, 2, 3, and 6. And factors of 9 are plus or minus 1, 3, and 9. So we're going to be dividing these terms by all of these. So I'm just going to, again, put the plus or minus out in front so I don't have to write it each time. So plus or minus 1, 2, 3, 6, all divided by 1, 3, and 9. So what does that really mean? That really means you're dividing all of these numbers, I'm just going to write it separately, by first 1. And then you're going to do plus or minus 1, 2, 3, and 6 and divide those numbers by 3. and plus or minus 1, 2, 3, and 6 has to be divided by the 9 because you're dividing by the leading coefficient. So that gives us plus or minus. First one would just be the same numbers, 1, 2, 3, and 6, because they're divided by 1. If we get anything repeated, we don't need to write it. So we have, in this case, I'll just write them all out for right now, and then we'll go through them again. So 1/3, 2/3, 3/3, 6/3, and then over here we would have 1/9, 2/9, 3/9, and 6/9. And then of course we can cancel out factors that we've already had. So 1, 2, 3, 6, 1/3, 2/3. We know 3/3 is just equal to 1, so we don't need that one. 6/3 is just equal to 2, so we don't need to write that one. 1/9. And then 2/9. And then 3/9 is equal to 1/3, which we already have, and 6/9 is equal to 2/3, which we already have. So these are the possible rational roots. And the reason we like to know the possible rational roots is because it's going to help us find all the rational roots. So the next thing we're going to do is find the zeros when the leading coefficient is 1, and then day 2 will be finding it when it's not. So the steps to doing this, you list the possible rational zeros, test them, then we're going to factor resulting polynomial if possible and solve for x. So for these, we're going to find all the zeros of this polynomial equation, and we want to find the exact answers. So for this, we have x cubed plus 3x squared minus 10x minus 24. So the first step is to list the possible rational zeros. So we want to do the same steps that we were just doing. So first we have the constant, which is, in this case, negative 24, and the leading coefficient, which is, of course, 1. So we want factors of 24, plus or minus 1, 2, 3, 4, 6, 8, 12, and 24. Again, if you need to use your calculator, you can, over plus or minus 1. So that means that the possible rational roots are plus or minus 1, 2, 3, 4, 6, 8, 12, and 24. Then for step 2, we are going to use our calculator. So you guys should get your calculators out and make sure you're practicing along, because these steps can be hard, and so it's good to practice them. So we're going to plug the equation into our y equals. So for our equation, we have x cubed plus 3x squared minus 10x minus 24. And now that I have that, I can go ahead and look at my graph. So I'm just going to do zoom 6 for a standard window. I might need to make it larger. We're going to use the fact that we know that for this is a polynomial degree 3. So odd positive means the right end of my graph goes up and the left end down. So I'm just not seeing the minimum here. So my graph looks like it goes like this, like a cubic function. I'm not really concerned about that because I'm not trying to graph this. I'm just trying to look at my x-intercepts. So here we're going to use our possible rational roots and test them. So it looks like if I just look at my graph, negative 1, negative 2, negative 3, negative 4, so negative 2, negative 4, and 1, 2, 3. So I can do second trace value, and I can plug them in, negative 4, enter, and if I get a y value of 0, then we know that it's an x-intercept. Second trace value, if I do negative 2, enter, I get 0, and second trace value, if I do 3, enter, I also get 0. So those are the actual rational roots of my graph. Another way that we can do that is we can use our table. So if I go to my table, I can look at the y values there. If it's not a nice number such as we have right now, what if you have decimals and fractions, then you can use ask. So you could go ahead and put for the independent on ask, and then go to second graph, which is your table, and plug them in this way and test them. So you could test all the values. Like if I did 1, notice I get negative 30. If I did negative 1, I get negative 12. So that's how we know those are not actual rational roots. But when I plug in negative 2 or negative 4 or 3, those all give me zeros, which means they're the solutions. So the actual roots are x equals negative 2, negative 4, and 3. And again, I use the second trace and then number 1, which is the value to help me with that. That doesn't always happen, that you're going to get the actual roots from the whole list, and we'll talk about that in a little bit later. So that means we need to figure out how to find all the solutions when I don't have that. And I also want to be able to factor this polynomial equation. So the next step would be to factor the resulting polynomial if possible. And we can actually use our roots to factor. Because remember, if these are solutions or roots, that means they're also factors of the equation. So really, I can just write these as factors. I know it's going to be x plus 2 times x plus 4 times x minus 3. But again, we're just going to show the steps so you guys can get used to it. So we're going to use synthetic division. So you can pick any one of these. It doesn't matter, negative 2, negative 4, 3, any one to do the synthetic division. So I'm going to use my polynomial coefficients, 1, 3, negative 10, and negative 24. Bring down the first term. Remember, we add them. So 1 times negative 2 is negative 2. Add these together to get 1. 1 times negative 2 is negative 2. Add these together to get negative 12. Negative 12 times 2 gives us 24. So that means the remainder of 0, which we know should happen because we know it's a factor. And then, so we have x plus 2 is the factor. And then this gives me x squared plus x minus 12. And then we know we can factor that further. So x plus 2 times factors of 12 that add up to 1 would be x plus 4 times x minus 3. And we already knew that was going to factor because we already had all the roots. But again, I'm just showing you for when it doesn't happen that way, how we go ahead and do this. And so you might be asking, why didn't we do factor by group? Because we learned that if we have 4 more terms, we can do factor by grouping sometimes. So remember, that's when you group the first 2 terms and the last 2 terms and take out the GCF. So here, the GCF would be x squared. So if I take out x squared, I get x plus 3. Here, if I take out negative 2, I get 5x minus 12. But notice these are not the same, so that means we can't do factor by grouping. And that's why it's important to know how to do the synthetic division to factor your polynomial, and then you end up with a quadratic that you can either use a quadratic formula or factor further. If you end up getting all the roots, for now, just practice these steps. Even though we know these are all the solutions, it'll help you later. But if this was like a final exam or something, you can just stop right here at the actual rational roots. And of course, after getting, this is of course the factored form, you would set them equal to 0 to solve. So we already knew that the actual roots are negative 2, negative 4, and 3. So let's go ahead and do another one. So we have this polynomial equation. So this is again a degree 3, which means we should have 3 answers. So we're going to do step 1. So for step 1, it's factors of the constant, which is 7. So plus or minus 1 and 7 over the leading coefficient, which is 1. So plus or minus 1. So that means that the possible rational roots are plus or minus 1 and 7. And then the next step is to plug it into your calculator to find the actual rational roots. I'm just going to always label it ARR. So these were the possible rational roots. The actual roots we can use our calculator to find. So if I go to my y equals, we have x cubed minus 3x squared plus 3x. And then plus 7. And hit graph to look at the graph first. So if I look at my graph, now notice that I only see one x-intercept on my graph. That means the other two have to be imaginary because this is odd positive. The left end goes down, the right end goes up. So second trace value, if I plug in -1, I get the y value 0. I could also use my table if I want to. So the actual rational root that we found is x equals -1. So remember, this is only finding rational roots. It's not finding all the roots. We need to find all the solutions. And since this is degree 3, we should have 3 solutions, which means that the other two are imaginary, since we could not see them on the graph. So now we can go ahead and do step 3, which is our synthetic division using the actual rational root to help me factor my polynomial equation. And again, that's because if you try to do factor by grouping, you're going to see that this does not factor by grouping, because if we do grouping here, you can take out x squared, and that gives us x minus 3, and then here you can't take anything out, so then that again shows that we can't do the factor by grouping, so that's why we have to do our synthetic division. If you could do factor by grouping, of course that would be faster. So -1 comes out, so this becomes 1, -3, 3, and 7 for our coefficients. We weren't missing any 0 placeholders. Of course, if you are, make sure you write them in. -1 times 1 is -1, so that gives us -4 when we add those together. -4 times -1 is 4. Add these together to get 7. That gives us -7, so the remainder of 0, which should work because, again, this is an actual root. And then from here, we can write our factors. So this is a factor, of course, is x plus 1, and then we get x squared minus 4x plus 7. And so for this, if you try to find factors of 7 that add up to -4, it does not factor. So how do I find the solutions when it doesn't factor? Remember, we use the quadratic formula to factor or find the solutions. So we have x plus 1 equals 0 and x squared minus 4x plus 7 equals 0. So we already know this one is x equals -1. Over here, a is equal to 1, b equals -4, c is equal to 7. So we get x equals -4 plus or minus the square root of -4 squared minus 4 times 1 times 7 all over 2 times 1. And of course we want to find the exact solution, so we're going to go ahead and simplify. So we get 4 plus or minus the square root of 16, because remember, negative squared is positive, so be careful if you use your calculator to plug that in that you use parentheses. Minus 4 times 7, which is 28. And so then when we do that and simplify, we get x equals 4 plus or minus the square root of -12 over 2. The square root of -12 is I root 12, and root 12 breaks down into 4 and 3. So this breaks down into 2 and 2. So this is equal to 2I root 3. All divided by 2, and then we can keep going because we can divide both these terms by that 2 and simplify to get x equals 2 plus or minus I root 3. So the roots, or the zeros, are 2 plus or minus I root 3 and -1. And of course, you could write them separately if you want. If you want to write it as x equals 2 plus I root 3, 2 minus I root 3, and -1, that's fine. It doesn't really matter. And we know that we're finished because we have 3 solutions, which is what we were looking for. All right, so the next equation, if I look at question number 5, we did not talk about how to factor 1, 2, 3, 4, 5 terms, which is a polynomial. So this is a degree 4, which means that we have 4 solutions that we're looking for. So degree 4 equals 4 solutions when we are done. So step 1 is going to be to list the possible rational roots. So we have factors of the constant, which are factors of -90 over the leading coefficient, which of course is 1. So that would give us plus or minus 1, 2, 3, 5, 6, 9, 10, 15, 30, 45, and 90. All of that's being divided by 1, so that's just going to give us the same thing. So these are our possible rational roots. And again, remember, you can use your calculator to find those if you need help. You could always go to your y equals and plug in 90 divided by x and use that to help you figure out what your factors are. But of course, we changed our table, so second window, you'd have to put it back on auto and then go to the table and look at them, starting at 1. So now that we have our possible rational roots, we're going to use that in the graph to help us figure out which are the actual rational roots. So that means now we're going to go to our y equals and plug that equation into my y equals. So x to the 4th plus 3x cubed minus x squared plus 27x minus 90. And hit graph. So this is even positive, so both ends of my graph should be going up. So it looks like both ends are going up. We just can't see the minimum value there. So if you wanted to zoom out to make sure that that's the way that the graph is going, you could just go to zoom and just keep hitting enter. And then you could try to look for where that minimum value is. But then if you look, the more you make your graph go in and out, the harder it is to tell those zeros, and we're not really concerned with that. We're more concerned with, well, what is our x-intercept? So I'm going to go ahead and zoom back in. So it looks like we have -1, 2, 3, 4, 5, and 2. So let's go ahead and check. Oops. So let's go to second trace value, -5, enter, that's an x-intercept, and second value trace, 2, enter, that's also an x-intercept. Again, you could do second window and put it on ask and then put the values in that way and check all the possible ones, but it's just not necessary because it's a lot easier just to look at the graph and look at the table values. So now that I know the actual rational roots, so the actual rational roots that we found were x equals, we said -5 and 2. That means that the other two solutions must be imaginary. So for this, we're going to use synthetic division. It doesn't matter which one you pick, you can pick either. So if we use our synthetic division, I'm just going to go ahead and do -5 first. So we have 1, 3, -1, 27, and -90. We can bring down that 1 and multiply, add these together, multiply, and then add, multiply, and add, and then multiply again. Remember, your remainder should be 0. If you don't get 0, that means that you did something wrong. Look at it again. Either look at your synthetic division, look at what you plugged into your calculator. Often I find students plug the equation incorrectly to the calculator a lot of the times, or they did synthetic division incorrectly. So now we can write the factors. This is x plus 5, and then if this is degree 4, that means we start off with degree 3 here. So x cubed minus 2x squared plus 9x minus 18. And then we can keep going using the other root that we did not do. So we don't want to use the original polynomial equation. We just factor that. So if we're going to use the second root, we factor it using the equation that we just found from our answer. So we're going to use synthetic division with the other 0. Using that answer. So for this, we have our other root, or 0 is 2. And then now we're going to use these coefficients, 1, -2, 9, and -18. Because again, we're just factoring it further. 2 times 1 is 2. This gives me 0, 0, 9, and 18. And again, notice that my remainder of 0, which should happen. If it doesn't give you 0, then you did something wrong. So now we have our factors. We just bring this over here. So x plus 5 from before. This factor gives us x minus 2. And then here, we started off with degree 3. So this is x squared plus 0x plus 9. So this is the factored form, and we're trying to, of course, find the zeros. So we get x equals -5 when we set that equal to 0 and solve, and x equals 2. And here we would get x squared plus 9 equals 0. So x squared equals -9. So x is equal to, don't forget to take plus or minus the square root of root -9. That means this is imaginary. So plus or minus I root 9, which is equal to plus or minus 3i. So that's 1, 2, 3, 4 solutions. So that means our zeros, or our x-intercept solutions, are roots. All those words mean the same thing. Our x equals -5, 2, and 3i, and -3i. Of course, you could write it as plus or minus. It doesn't matter. Okay, so that's not the only way we could have done this. So that's if maybe you don't remember how to do your factoring, but over here on this answer, we could have done factor by grouping. So I could have taken this answer right here. So we had the x plus 5 times x cubed minus 2x squared plus 9x minus 18. So I could have done factor by grouping on this portion right here. And that works for 4 terms. We group the first 2 and the last 2 terms, take out the GCF. So that gives us x minus 2. Same thing over here. The GCF is 9, and that gives us x minus 2. Because these are the same, we can group them together. So that becomes x squared plus 9 times x minus 2, and then you bring down the x plus 5. Notice that this factored form is the same as what we got over here when we did the synthetic division. It's just another way of factoring. So if you can factor it and you know how, that's usually a lot faster. But let's say you forget how to factor, you could always use your synthetic division, because remember, if you get a remainder of 0, that means that is a factor of the equation. So both of those are the factored form, but that question was to find the zeros, so here are the actual roots. And then we're going to practice some more of this tomorrow without the coefficient in front being 1 for each of these. So the leading coefficient that we used was 1, so we'll do some without 1. And we're also going to look at some that have irrational roots. So that means that you're going to be able to see other roots on the graph, but in order to find them, again, you're going to have to use synthetic division.